Okay, so should I start, Andre?
Yes, please.
Okay, so thank you very much for inviting me to this fascinating conference. It's a real honor to be here. So what I want to talk about is something I've been kind of obsessed by during the pandemic. It is a class of unusual four-dimensional quantum field theories which have no supersymmetry, but which appear to have many properties in common with two-dimensional integrable theories. So you might ask, well, why I'm interested in these things? Well, these models are non-normalizable. So normally people would say that non-normalizable 4D Lagrangians are just junk. There's too much ambiguity in building the theory at the quantum level to do anything meaningful. But these particular theories, by using twistor space, we constrain the counterterms very tightly. So we get a family of 4D theories with the following very strange properties. So the first property is that the orgy flow is periodic with imaginary period. This is a property I can prove in perturbation theory. The second property is they have some analog, not quite fully understood, I have to say, of the Yang-Baxter equation. So they have strings, and they scatter in a way where an equation like Yang-Baxter holds. The third feature of these theories, which I was really excited about for the past couple of weeks, is that the celestial logography program, which aims to describe the symmetries arising from soft theorems in terms of chiral algebras, works really beautifully. And so I've been working a bit with this on Natalie Piquet, and we conjecture, and we have some evidence, that in this case, celestial logography is the same as twistor tomography, which is something I was studying with Natalie, and with Davide Gaiotto, and with many other people I've studied. So to start, I think I will, one sec. I'll start by reminding people a little bit about background on what twistors are. So twistors have appeared several times in this conference, so I hope people are reasonably familiar with them. So twistor space, that's introduced by Penrose, is the following complex threefold. It's just O1 plus O1 over CP1, and it's an open subset of CP3. Now, as a real manifold, it's simply a product of OR4 and CP1. So this means we could take a theory on twistor space and dimensionally reduce along the CP1 to get a theory on OR4. I'm going to be interested in holomorphic theories in twistor space, things like holomorphic Chern-Simons. But because this factorization as OR4 times CP1 is not as complex manifolds, but only as real manifolds, when we reduce to OR4, they'll become ordinary theories in OR4. Ordinary, but very interesting theories in OR4. So it's important to mention that this procedure of dimensionally reducing from twistor space to OR4 is much more robust than the familiar KK reduction. There are no KK modes, so that the reduction procedure is just exact. The reason is holomorphic theories don't require a metric to define them. The metric only appears in the gauge choice. So the size of CP1 is only a gauge choice. So we get the same thing if it's big or small. And it's possible to make this argument completely mathematically rigorous in perturbation theory. Okay, so how can we build holomorphic theories in twistor space? Let me give some examples. So this kind of thing was, of course, studied many, many years ago by Penrose. And one basic example is the Penrose-Ward correspondence, which you can formulate as saying that holomorphic BF theory in twistor space is self-dual Yang-Mills at OR4. So self-dual Yang-Mills has this very simple Lagrangian where B is a self-dual 2 form. And if we were to add a BB term, this would become full Yang-Mills. Okay, so another famous example is the Witten-Berkowitz proposal for the twistor string theory. They show that holomorphic Chern-Simons on a superversion of twistor space becomes self-dual n equals 4 eigenvalves. And to get away from the self-dual limit, one has to study the D strings. This was generalized by Bowles, Mason, and Skinner, and they discussed versions of this with less supersymmetry and matter. And a really beautiful example is Penrose's nonlinear graviton construction, which gives self-dual gravity, and that was extended to the supercase by Mason and Wolf. So these are all like beautiful examples. However, they all have one big defect. They're one loop exact. So perturbation theory stops at one loop. So they're kind of close to being free. So I'm interested in theories which are like that, but a little more rich. So I want to study something which does not stop at one. So the first class of models I want to mention is holomorphic Chern-Simons theory in twistor space. So holomorphic Chern-Simons theory is a simple Lagrangian. I take the Chern-Simons Lagrangian for a 0-1 form and a Calabi-Yau, and I wedge it with the volume form. Twistor space is not Calabi-Yau. However, it has a meromorphic volume form, which here I've written in coordinates, where Z is the coordinate on the base and VIs are on the fibers. Now, it turns out that this holomorphic Chern-Simons theory, and indeed the associated topological string theory, makes sense as long as we impose suitable boundary conditions on the gauge field, on the gauge fields at the locus where the volume form is a pole. So I announced a result in a talk a while ago, and a lovely proof was given by Biddleson, Skinner, and Penna, is that if we built this holomorphic Chern-Simons theory, then the corresponding four-dimensional theory is the Wzw4 model, which was, I think the Lagrangian was first written down by Donaldson, but it was studied in detail by these authors. And it's a very simple and beautiful, in my view, model. So it's a natural deformation of the four-dimensional sigma model. The fundamental field is a map to the group. And the Lagrangian has two terms. First term is just the usual sigma model Lagrangian. And the next term, well, what it is you note that the sigma model in dimension 4 has a topological U1 symmetry associated to pi 3 of the group. You know, I can think of a three-sphere which wraps multiple times the group. So I can couple that to a U1 gauge field. So the next term is saying I just put a background U1 gauge field whose field strength is the Kähler form. And these coefficients have to be normalized correctly, and it gives you a very nice model in 4 dimensions.
What is J?
J is the current. So if we reduce to 2 dimensions, Biddleson and Skinner and Penna show that it becomes the principal chiral model. Because this model, the Lorentz group is broken, what we get in 2 dimensions depends exactly how we reduce. So turns out that there's a single parameter in the way we reduce, and that matches the parameter in the principal chiral. Okay. So this is all fun, but it's all classical. So it turns out it is pretty difficult to construct a field theory in twistor space. Most of the time, the classical field theories people have written down for many years just don't exist. Well, the one for n equals 4 self-dual angles does exist, actually, but many of them don't. The reason is holomorphic theories in 3 complex dimensions can have one-loop anomalies associated to box diagrams like this. So one can do explicit Feynman diagram calculations. We use the local index theorem, and you find that the gauge variation of such a diagram will look like this kind of thing, where I take trace of the derivative of the trace of the field strength cubed times the gauge parameter. Fortunately, sometimes these anomalies can be cancelled by using a topological string version of the Green-Schwarz mechanism. So that happens when the group is SO8. The reason is there's a certain trace identity with the group SO8, similar to the one needed for the hexagon diagram in the familiar Green-Schwarz mechanism for SO32. So in this case, the anomaly associated to the box diagram cancels with the exchange of a closed string field. So here's the proposal that in the whole universe of all possible 40 QFTs, there's some tiny number which lift to local field theories in twistor space. So the main example I'm interested in today is Wzw4 for SO8, plus the closed string fields. And there's a couple of other examples. Basically, one can think about engineering examples by studying anomaly-free string theories, taking a supersymmetric sector of them, compactifying it to twistor space. So that gives you a bunch of examples associated to, for example, associated to free folds fibered over P1 where the fibers are K3s. We'll give you a task examples. My favorite example is associated to topological strings on a version of twistor space built from a genus 3 hyperelliptic curve. I won't have time to talk about that. Okay. So one can ask, what are the closed string fields? It turns out, on twistor space, it's given by a version of Kodaira-Spencer theory. And if you analyze what that becomes in real space, the fundamental field of Kodaira-Spencer theory is a 2-1 form. I can take its primitive and view it as a 1-1 form and integrate it over a CP1. I get a scalar field on real space, which I'll call rho. And this scalar field should be interpreted as the Kähler potential. The reason is the Wzw4 model is defined on Kähler manifolds. So it has a Kähler stress energy tensor, which I can couple to a 1-1 form. And if you compute how it's coupled, dd bar rho does indeed couple to the Kähler stress energy tensor. But it also has some self-interactions in kinetic term. It has this weird fourth order kinetic term, Laplacian squared. And this interaction, these dimensions and symmetry will tell you that these are the only two possible terms, and then you can compute the relative coefficient. Looks like that. I was unable to compute beyond cubic order, so I don't know what happens to order 4. It turns out that the equations of motion are that this, at least to the order I can compute it, are that the scalar curvature of the modified metric vanishes, or is proportional to dd bar of the Kähler stress energy tensor. So that is, this model is a simple model coupled to gravity, and it comes from a local theory on twistor space, and I'm claiming it has a bunch of nice properties. Let me see what the properties such theories have. The most important one is that though it's non-normalizable, the counter terms are uniquely defined. The reason for this is that most of the counter terms you might imagine writing down are not local on twistor space. Say for a scalar field, phi to the n is n local. I have to integrate over n points on twistor space. There's a very tiny number of actual local counter terms. So some years ago, not that long ago, C. Lee and I proved that Holmford-Simons plus Kodaira-Spencer theory for SO8, the counter terms are uniquely fixed by asking that there's no anomalies. So this tells us that Wzw4 plus the gravitational field has a canonically defined quantization. Sorry, I should stop at 11:10. Is that right, Andre?
Yes, you still have 9 minutes.
Oh, 9 minutes. Okay, good. Okay. So another important property is that the org flow is periodic. So let me explain why this is. Org flow is, I'm simply scaling space-time by a real number. On twistor space, I can scale space-time by a complex number because all we do is we multiply the fibers by an element of C star. Because it's a holomorphic theory, everything depends holomorphically in how I scale it. So it's very, very formal and trivial argument that tells us any holomorphic theory on twistor space gives rise to a theory on O4, where the dependence on the scale extends analytically to C star. This implies there can't be any log divergence. It also implies any familiar theory, essentially any familiar theory, cannot arise as a local theory in twistor space, with the exception of CFTs. So Wzw4, I mistakenly claimed that there was a one-loop divergence cancelled by Green-Schwarz at a different talk. This turns out to be incorrect. The right result is by Wzw4, that the first divergence can happen at 2 loops. Okay, so I'll try and move a little faster. So these theories, because they come from theories in twistor space, holomorphic theories, topological strings, they have D strings, just like in the original proposal of Berkovitz and Witten. So these D strings can wrap a curve in O4, and they're really strings because their position is dynamical. Now, very simple formal arguments tell us that these D strings can't touch, that because they don't touch in twistor space, we can move them past each other without introducing any singularities. And similarly, I can move them past each other in this way. It turns out this is something you can check that only works because of the Green-Schwarz mechanism. I believe I can show that this fails at 2 loops without the Green-Schwarz mechanism. Here's my hope. So these 4D theories, which have these D strings satisfying a Yang-Baxter-like equation, are just as nice as the familiar 2D integral models. So I was unable to really compute anything about the scattering of strings, but I would really, my dream is that it's solvable in the same way the 2D models are. So this is really a hope. So the last 2 minutes, I want to explain quickly a little bit about what we're looking at with twisted holography and celestial holography. So in twisted holography, well, we build a chiral algebra controlling scattering of states in some supersymmetric subsector of n equals 4 Yang mills. So the basic example is we take SL2C, which is ADS 3 times S3, and on the boundary of ADS 3, there's a chiral algebra, and the OBEs describe scattering. So we can do the same construction for twistor space. We can build a chiral algebra by studying states sourced by operators at infinity, and it works just the same. And the conjecture is that this chiral algebra just is the same chiral algebra as people studied in the celestial holography literature. So we computed this. We start with self-Julian Mills theory. We do this computation. We get exactly the same algebra studied in this paper. Probably, I haven't done the computation, but it's probably true with the gravitational sector as well. Of course, this is anomalous. This theory is anomalous, as I mentioned. I'm not quite sure what that means for the celestial holography proposal. For the Wzw4 model, if we run the algorithms from the celestial holography literature, then we do find that the states they write down of negative dimension are exactly the states sourced by the single particle primaries in our chiral algebra. When we can compute the tree-level OBEs, they seem to match. In this case, we can also go beyond tree-level, though. There's a nice computation by Lorgat, Musavi, and Joe. They computed some subleading correction. It's no longer a Lie algebra. leading to the possibility that the soft theorems at the loop level may be described by these kind of strange Yangian-like quantum groups. Okay, I think I should stop there. I'm a minute over. I'll put the last slide up, but I want to read it.
You are not over.
I'm not over? Oh, okay, sorry.
Allow it to speak one more question.
Okay, so let me do the last.
You have 3 more minutes.
Okay, well, why don't I read the last sentence? So I was going a little fast because I really thought I was over. So these examples, it's also fun to think about back reacting a D1 brain. And this will bring us to a situation much closer to usual holography. We do this in twistor space. What it will become is like some quotient of SL2C by the integers union some stuff. We can ask what happens in real space. If we place a vertical D1 brain over the origin, it back reacts by changing the Kähler potential in this way. I add on log of the radius. So it's natural then to conjecture that if we take this Wzw4 model into back reacted geometry, the chiral algebra, which controls scattering of states, is exactly the large end limit of the chiral algebra on ND1s. This chiral algebra is known in the literature. It appears for a certain family of n equals 2 theories with SO8-favored symmetry. Okay, so I will stop there, and I hope my talk was not too fast to be coherent.
Thank you very much, Kevin. Let us see if there are questions. Yes, Hiroshi has a question.
Yeah, so I have a question. So I'm assuming that you are doing quantization in 6-dimension twistor space rather than 4-dimension. I think there is a distinction between them, even though there are no Karuta-Klein mode, because there could be different on-share degrees of freedom. And you said that almost all counter terms local in 4 dimensions are non-local in the twistor space. I think that's the reason why you say that this is partially non-renormalizable, but still makes sense. But could there be counter terms that are local in the twistor space?
Asking, are there any counter terms that are local in twistor space?
My question is that could there be counter terms that are local in the twistor space? Because you said that you do not have to worry about counter term in 4 dimension because almost all of them are non-local in twistor space. But if you are quantizing in 6 dimensions, should we also be worried about other types of counter term?
I suppose the issue in 6 dimensions is more with anomalies, and because it's, in 6 dimensions it's a gauge theory, whereas the gauge symmetry is broken when you go to 4 dimensions. So the question of whether there are counterterms are you look at the algebra of local operators, which is entirely concentrated in positive ghost number, and you're interested in things of ghost number 3 because you want to descend them 3 times. Or of ghost number 4, because they will contribute to anomalies. And so there's some cohomology computation, which is quite challenging. So, but it seems like there, so we did these computations with C. Lee, and we found there was nothing in the relevant ghost numbers, except for the Green-Schwarz, except for the box diagram anomaly.
So in the direct 6-dimensional analysis, there are no conceivable counterterms. Is that a statement?
Yes, but only when you couple the open and closed string sectors.
Okay. So anomaly guarantees that there are no counterterms.
Yes.
Thank you.
Mykola.
I have 2 quick questions. So first, silly question. I missed, what was the PCM in your slides? What is the, what does it mean?
Sorry, but it's principal chiral model.
Okay. And you said that the RG flow is periodic with period 2 pi I. Is there like some scale because it's a dimensionless number? What does it mean? There's a period 2 pi I.
I mean, it means something very simple. Like if this is a statement in perturbation theory, and if you look at all of the counter terms, they're functions of the cutoff, and you try to extend them to analytic functions of the cutoff, and they have no branch cuts. That's what it means.
Okay.
Question from Atul. Atul Sharma.
Yeah, I wanted to ask, in the gauge theory case, in the 4D Wzw4 case, you can at least, from what I understand, start with D6D theory on twistor space and exactly compactify on CP1 and get the only interaction that you get a J cubed interaction, no higher order terms. So what is your procedure for the corresponding scalar case that is generating all these higher order tower of terms?
Yeah. Well, I think it's a little misleading to say there's no higher order terms, because the Wzw4 Lagrangian takes such a simple form because you've written it as an element of the group instead of the exponential of an element of the Lie algebra. It's like the element of the Lie algebra is what corresponds to the 6D gauge field. And if you expand it in terms of the logarithm of sigma, it's a huge series. So anyway, so my procedure here was, I found it pretty challenging to compute directly. So what I did was, I know that whatever you do, if I take the OPE of this scalar with its derivative, this is going to be analytic in X. So it's not going to have any logs. And then you compute, like, each of these terms separately introduces some log, and you have to arrange the coefficients so that it cancels. And that method will continue as you go further if you want to, but it becomes more challenging.
Oh, I see. So you haven't started with a 6D theory for the scalar, like the Chern-Simons theory for the gauge case.
No, like there is a Lagrangian. I mean, it's kind of stupid that I wasn't able to do it directly. In principle, you could do the same procedure you do for the Wzw4. I just found the direct analysis kind of challenging, so I took this shortcut.
Sure, thanks.
Question from Edward Witten. Unfortunately, only 1 minute or so.
What would your Lagrangian have been in 6 dimensions for the gravity?
Sure, it's so the fundamental field is like a 2-1 form.
Yes.
Which I can also view as a Beltrami differential with certain zeros.
Yes.
And then I just do the usual kind of Kodaira-Spencer thing. So you take literally the usual Kodaira-Spencer Lagrangian for a Beltrami differential. And then you notice that if I started as a 2-1 form, I turned it into a Beltrami differential at a certain zeros, and those zeros cancel any poles in the 3 form. So it makes sense.
And that leads to your theory with the row in 4 dimensions.
Yes. So the reason is there's a constraint in Kodaira-Spencer theory called eta, that this is closed, so I can take the integral over P1 del inverse eta, that's rho. And then you can compute explicitly the 2-point function of that one itself, and you find that's log, and that tells you that this has to be the kinetic term. And I found the interaction challenging, but I did this kind of procedure that I knew it had to be analytic. So.
Thank you.
I think that unfortunately we have to proceed to integrability discussion. Thank you very much.
Thank you.
Before we start, let me remind that people are, of course, welcome to continue asking questions on Slack, on the Zoom chat, or during the discussion. After all, this is an integrability-like theory, so I hope we can continue there. So.